Hello and welcome to the lecture on fluids in motion. Okay, so here instead of talking about fluids at rest and their pressures and densities and the buoyant force, instead we're going to talk about how we can understand the motions of fluids in a simplified manner using some laws of conservation. Okay, and we're used to conservation laws. Think conservation of momentum, conservation of energy. Okay, all right. So let's get to it. Let's get some definitions out of the way. There's actually quite a few definitions, especially for a later section in a chapter, because this is kind of a standalone topic. So first of all, our first key term, laminar flow. What is laminar flow? It's a weird word, laminar. Okay. Well, what you need to know is that it's an ideal, steady movement of fluid. So really, it's the type of flow we're only going to be talking about. It's a simplified type of flow. All right. Now, what's some of the background? Well, it's based on the idea that fluid consists of layers called lamina that move past each other. So it's like almost like layers of molecules. And that actually is one of the ideas that separates a liquid from a gas. It could be a gas if it's a very high density gas, but the idea is that you have these kind of sheets of molecules that sort of move independent of one another. They kind of ride on top of each other. It's obviously, an idealized model. That's not quite how molecules work, right? Okay. In such type of flow, in laminar flow, there's no turbulence or eddies/vortices. Okay. So it's super steady flow, right? And so in reality, the only time you really ever see it is very slow flow or really viscous fluids, like lava or honey or something just moving at a really, really slow rate. Those would be examples of laminar flow. All right. It turns out also things at a really small scale tend to have laminar flow, like the micron scale. But that's the flow we're talking about here. This is our idealization. All right. So streamlines are the visual representation of laminar flow. Okay, well, all right, that's great. What do we use them for? Well, streamlines are a quick way to see changes in velocity and pressure. For example, when streamlines are closely packed, this is high velocity and low pressure. We'll talk more about why those two go together. But here's a little picture, right? So here's the idea. This would be like flow in a pipe. These are the streamlines. They're not vectors. They're just lines. We put little arrows on them periodically just to show that they're flowing in a particular direction. Here the pipe is narrow, so the streamlines are closely packed together. Closely packed together means high velocity, right, in this region. If you have high velocity, that means you must have low pressure. Okay, again, more on that later. When the streamlines become widely spaced out here, that denotes low velocity. If you know it's low velocity, then you know it must be high pressure. Okay? And so they're kind of like topomap lines, topography lines. When they're far apart, that means it's slow or gradual. When they're closely packed together, that's steep or fast. Okay? All right. So one important rule, and there's a few other rules we don't care about so much, but one thing of note in this class is that streamlines can never cross. So you're never going to see them cross. That's a definition of what they represent. And that part of the reason is because they represent continuity of flow. And if flow is continuous, then it can't cross. It can't just appear and disappear. But what does really continuity mean, right? Maybe flow is continuous, but we need a formal definition. It means conservation of mass for fluid flow. So when fluid moves, you can't just have mass appear or disappear out of nowhere. It states that mass flowing per time, so that would be kilograms per second, past one point must equal the mass flow per time at a later point, since the mass cannot disappear or appear. It's conservation of mass, right? You can't just have mass out of nowhere. All right? And when flow paths, when they split, like in pipes or tubes, or merge, the continuity still applies, right? And we'll have to see an example of that, because in that case you would just kind of have a still continuity, but you'd have to sum up all the splits, or maybe if a bunch of things flow together, you'd sum all the things that flow together into that one new, kind of combined flow. All right. Now, two last things: the big thing, Bernoulli's equation, and then the less important thing, Torricelli's theorem. So, what is Bernoulli's equation, right? Well, it is conservation of energy for fluid flow. And by the way, this section in practice and what the quantitative examples we're going to be doing are mostly using these two, continuity and Bernoulli. That's what this section is all about, using the two equations that are associated with these two conservation laws, which shouldn't be a big surprise because, again, we've seen conservation laws. Conservation laws are super helpful. They're super useful. And here they're simplifying a system that honestly is a lot more complex than we're giving it credit for, but we are taking a simplification that is utilitarian. We can make use of it. Okay, we can get a good model. Right? But again, the whole deal of fluids is that we've taken a step away from really, basic systems here. Okay? So conservation of energy for fluid flow, Bernoulli's equation. Okay? Bernoulli's equation can also be derived from Newton's laws. I'm not going to derive it using energy or Newton's laws. I just want to point that out, that it's not coming from nowhere. And it also should make sense that if it is an energy conservation law, it should also be based on Newton's laws of motion, because ultimately any conservation of energy, even when we saw the mechanical energy, gravitational potential becoming kinetic, that was all based off of work. And the work kinetic energy theorem, and work itself comes from forces and is based on absolutely Newton's 3 laws of motion. So you really, the starting point is always Newton's 3 laws of motion. Okay, but it's an energy conservation law. And this conservation equation takes the form of balancing terms that have units of pressure. And that's kind of interesting because we made a big deal, okay, it comes from forces, it's about energy, but the actual terms in the equation have units of pascals, they're pressure terms. And I want to go ahead and show that to you. Of course, the equation will come up again on the key equations, but here it is, all right? It has 3 terms, and then we see the 1, there'll also be a 2, because it's all about balancing the 2 sides of the equation. But each of these terms are pressure terms. Now, there's a way to kind of immediately see that, because obviously P stands for pressure. Pressure must have units of pascals, of course, which are just newtons per square meter. And if one term has those units, and you add another term, it must have the same units. But of course, it's not immediately evident at first pass. Think 1/2 times density times velocity squared has units of pascals. But it does. And in fact, let's run through it. So density is kilograms per cubic meter. And then velocity is meters per second. All right. And we're squaring it. So we'll cancel out some of the meters. So we'll be left with 1 below. So then we're going to have, we'll have kilograms per meter per second squared. All right. And so we think about that. Okay, well then, force, what is force, right? Force is kilograms meters per second squared. Well, when you divide by square meters, then pressure becomes kilogram meters over seconds. All right, well, over seconds squared. And that's exactly what we're left with when we have 1/2 rho v squared. So indeed, this has units of pascals. Okay? Test it yourself, right? Make sure you see how that works. It's good to check units, especially when you have odd looking expressions like this. And this we've seen before. This is hydrostatic pressure. Right? Here are the labels. So we can call this gauge pressure, call this one dynamic pressure because it's got the velocity in it, and we'll call this one hydrostatic pressure because, again, that's a pressure that's due to depth. Okay? Again, refer to previous notes on that one. All right? So, interesting thing, in practice, the gauge pressure is often taken to be dependent on the other forms of the pressure. So usually, the fluid is moving, the fluid has a certain depth, and that's going to result in a gauge pressure. But that isn't necessarily the case. The gauge pressure could be independently controlled. You could exert pressure on the system and force the velocity to change. Right? But most of the examples, the gauge pressure is the thing that you find that's dependent on the other factors of the system. Okay? All right, so finally, Torricelli's theorem. All right, so what is that? Okay, it's not one of the big two. It's not one of the backbones of this section. It's more of a simplification that doesn't come up that much. Okay, so it's a simplification of fluid flow. It's a system like this. And what's specific about this system is it's maybe like a really big tank with a very large cross-sectional area and a small hole poked at some point below the water level. It doesn't have to be at the bottom, but it just has to be some depth down below the water level. And so it applies to fluid flow, Torricelli's theorem does, out of a small hole in a large container where the area of the container, A1, is much, much greater than the area of the hole. All right? So when that happens, all right, and oh, by the way, also to make Torricelli's theorem work, it has to be open at both ends. So this has to be like an open tank, and the hole has to be open too. It's not flowing into a hose or a tube or anything. It's just, you literally just poked a hole. So it's open to the air. So you have air here and air here. And the important thing, that means that you have atmospheric pressure at the top, and you also have atmospheric pressure at the bottom, like pushing in, right? So that means it's the same external pressure at the bottom and the top, all right? In other words, it's the same gauge pressure at the bottom and the top, okay? So P1 equals P2, unchanged pressure, all right? So it's open to the air. All the pressures are atmospheric, okay? So then you simplify Bernoulli's equation. Again, jumping the gun a bit, but the result, I think, is interesting, and we'll see Bernoulli's equation in just a moment, and then we'll put it to use plenty of times in a moment after that. Okay, so what is it? What is the simplification? Well, what happens is, after all, this is Bernoulli's equation. Looks something like this, and here's that gravitational term. Here's the difference in the heights, right? So y1 minus y2 would just be h. All right, and here's the dynamic term, and the gauge pressure is gone because it was equal on both sides of the equation, so it canceled out. And so what happens is then when you solve for v, you get the square root of 2gh. That might look familiar. It should. I would love it if it does look familiar, because that is the same speed as a freely falling object dropped from a height h that you could get either with kinematics or conservation of energy. So that's actually interesting. Okay, again, it's a big simplification, but it tells you that for a small hole in a big container, the water is literally coming out with the same velocity that a rock would if you dropped it from the height of the depth that the water is coming out from. It's kind of neat, right? But again, it doesn't come up that much because it really requires, this idea that the area is much larger of the tank than the hole. Okay. All right, let's get to those aforementioned equations, or formulas. Not many of them, okay? So there's just the two. Okay, top one's continuity, bottom one is Bernoulli, okay? So, and they're all going to be kind of based on this idea. Mostly we're going to be considering flow in a pipe. Now we could definitely have like flow in a river, right? And we could have, the river getting narrower or wider, going over rapids, reaching a really deep, deep part of the river. But really, I think it's just better just to kind of stick to one system and think of pipes, right? So that's the idea, right? This is some circular pipe. And the whole idea is there's going to be area, there's going to be pressure at certain points, there's going to be changes in height, like we can see here. Positive y is always going to be defined as upwards. I'm going to reiterate that in just a second. And the velocities are going to be changing, and they're going to be at different points, right? So basically, there's everything happening at point 2, all right, and everything happening at point 1, okay? So this first one is, as I said, continuity. Now, continuity is a conservation of mass term, which means that these would probably be masses, and indeed they are, right? And they're mass flows, I should say. They're kilograms per second. That's the units here. We take density, you multiply it by area and velocity, you get kilograms per second. So this is the form that the continuity equation takes, a conservation of mass equation. Now, but here's the thing, the densities never change. They're going to change. We're not going to deal with compressible fluids. The density is absolutely constant, unchanging. And that means that it cancels out. So every time you actually see continuity, it's always going to be written as A1 V1 equals A2 V2 because the density canceled out. The only reason I even included it here and immediately cross it out is because I wanted to call attention to the fact that it is a mass flow rate conservation, all right? It's not a, because otherwise it would be meters squared, let's see, so this is meters squared, otherwise it would be a volume flow rate, right? Because this right here, these units are just meters cubed per second, all right? But ultimately, it's about conservation of mass, not conservation of volume, because who says the volume is conserved, right? Okay, but in practice, it's always going to be A1 V1 equals A2 V2. All right, so that's continuity, pretty simple. Now here's Bernoulli, all right? Oh, here's the terms, I forgot. This is just fluid velocity, and that's cross-sectional area, okay? Like this. This would be the cross-sectional area. All right, so now on to Bernoulli. All right, I always I always shorten it as Bernoulli rather than Bernoulli's equation, okay? And here it is. It's all about pressure terms. So there's pressure at point 1, or the sum of the gauge pressure plus the dynamic pressure plus the hydrostatic pressure at point 1 equals the sum of gauge pressure plus the dynamic pressure plus the hydrostatic pressure at point 2. Okay? All right. Here are the names. All right. And rho is obviously density, v is velocity, and then y is the height. Now I said I'd call attention again to the directionality. So since this is like a pre-derived equation, we can't, and we're not starting with the sum of forces, we're not starting with Newton's second law, we cannot choose which direction y points. This equation was derived on the assumption that positive y points up. So you can never change the direction of positive y, okay? Because normally we can. If this was a normal, even buoyancy problem, we can set the direction of positive y. We can define it whatever way we want as long as we're consistent. But since this is already derived for us, positive y has to point up, okay? Just a note of caution there, because otherwise you're going to get the wrong answer. All right, so now let's go on to our practice. Okay, a few types of problems, 3 types. So type 1 are quite simple. Simple problems that only require use of the continuity equation or Torricelli's theorem, right? So we don't need the Bernoulli idea at all. We don't, there's going to be no pressure involved. Type 2, problems that involve using Bernoulli's equation and continuity to solve for fluid flow values, okay? That's kind of the typical one. And then type 3, problems that have a little something extra. So they got Bernoulli, they got continuity, and they're combined with some other concept. And the only 2 other concepts we'll see is either projectile motion or lift forces. Okay? So we'll see what that looks like. Because you might be like, huh? How does that work? All right, so first of all, a simple example. Our ancestor, the sponge, has a series of intake tubes, it's all these little ones here, okay, that are lined with cilia, all right? Cilia are like little, like molecular motor hairs, used for trapping and digesting food. However, the sponge needs to avoid digestive waste product from building up inside of it, okay? So it has to eject its waste somehow. So the mini intake tubes converge into one central tube that creates a high velocity ejection jet, right? At least much higher velocity than the intake valves. If the number of intake valves is 620, and each one has an average intake velocity of 4.4 meters per second and a radius of 650 microns, okay, which is a millionth of a meter, and the single central tube has a radius of just 0.85 centimeters, okay, or 8.5 millimeters, then how fast is the excrement jet? Okay, let's see. So we're just going to use continuity here. So what we're going to do is we're going to take our intake velocity. We're going to take our intake area as the sum of the 620 tubes. So just multiply 620 by the cross-sectional area of a circle, which is going to be pi r squared. So here's the r squared, which is the 650 microns, 10 to the negative 6, squaring it, and then multiplying by pi. Okay? And then that's going to be equal to the excrement jet velocity times the cross-sectional area, again using the equation of a circle, pi r squared. All right? And here we have r written in meters with the 8.5 millimeters, squaring it, multiplying by pi. Okay? Pi cancels right away. And then we can go ahead and solve for V2. And when we solve for V2, we get 16 millimeters per second. All right? Because I went ahead and left this in millimeters. Notice I converted the other things to meters so that we'd have consistent units, importantly. But I left the intake velocity in millimeters per second, so my output one is also millimeters per second. Okay? So there's the idea. Okay? We have a about fourfold increase in velocity, helpful for pushing the water out. All right? And that's continuity at play, and with a bunch of little things combining into one big tube. All right? So let's consider now the relationship between velocity and pressure, okay? Because this is one of the big ideas that is a little tricky and potentially counterintuitive. So gas flows through a pipe. You can't see into the pipe to know how the inner diameter changes, but you can see these little tubes here that are either sucked up because there's low pressure, or they're not sucked up as much because there's higher pressure. So you could think of this as being the highest pressure because because maybe it's being pushed down a lot, and this one not being pushed down that much at all means that there must be really low pressure here at point 2. Okay, right? So right away we know that this one has P2 has low pressure, is low, right? Whereas P3 is quite high pressure, because it's pushing the fluid down. Okay, that's the idea here. Make sense? It's like sucking fluid up a straw, right? The bigger the vacuum you create in your mouth, the higher the fluid will get sucked up. Okay? Right? So that means that this one is closer to a vacuum. Okay. So rank in order from largest to smallest the speeds. Because again, we can essentially see the pressures, right? We can read this as pressures, but we want to relate that to speeds. How do we do it? Well, we can say that the largest speed, because we're supposed to be rating here from largest to smallest, so the first one is the largest, V2. How do I know that V2 is the largest just because it has the lowest pressure? Well, just in pure memorization, you can just say, oh, well, that's because velocity is inversely related to pressure. So the smaller the pressure, the greater the velocity. 2 has the smallest pressure because it's the closest to the vacuum. It sucked the fluid up the most. Okay, but why? Why should faster fluids have lower pressure? It seems like fast means high pressure, right? Because if I think of a hose and I squirt something with a hose, and then I increase the pressure of the hose, then I can push something, right? There's more force. But that's not what we're talking about. Because when I increase the pressure of the hose and I can push something, that's because I'm forcing the fluid to make a U-turn. Okay? We've seen that idea before. We've seen conservation of momentum of fluids and exerting a force on something, or even exerting a torque. Think the water wheels. Okay? So that is a characteristic that fluids can exert in terms of pressure. But that's not the pressure we're talking about, because the water is not making a U-turn here. Instead, the fluid, or water, whatever it may be, is just continuing on its way. We're talking about the pressure that is perpendicular to the motion. We're talking about the pressure along the sides of the tube through which the fluid flows. And that pressure does decrease as the velocity increases. You can see it for yourself. Hold up 2 pieces of paper, blow air through those pieces of paper, and the paper will get pushed in next to each other. Because what will happen is, as you blow fast air through the paper, you create a region of low pressure where the fast air is blowing. The ambient pressure in the room now is greater than the low pressure region that your blowing has created, and that causes the paper to push in, filling in that low pressure area, because there's a force differential. So you can just easily see it for yourself that fast moving fluids create low pressure. Okay? And the mechanism behind it is, if the fluid is moving slowly, then all the random motion of the particles, they're going to bounce into the side, and they have more time to bounce into the side. All right? Because they're moving along, and they could have more chances for collisions with the side. When they're moving really fast, the particles, they're kind of more spread out and they have less opportunities to randomly bounce into the sides. And that's what pressure is. It's the random motion of the particles pushing into the sides. And the faster they're moving as a whole, the less random motion there is pushing into the sides and the lower the pressure. All right? So faster fluid flow through a pipe means lower pressure on the sides of that pipe. Okay? All right. Now let's do our first big quantitative example. All right. So the Venturi meter is used to measure the speed of water flow in pipes in a similar way to how the pitot tubes measure airspeed around planes. Shown is a basic Venturi meter. The diameter of the wider section of the tube, A2, is 5.5 centimeters, and the narrow diameter, A1, is 2.07 centimeters. That's right here. All right. The gauge pressure measured on the left at P2 is 995 kilopascals, so 995,000 pascals. All right. Almost 9 atmospheric pressures, okay? That's the high pressure there. And on the right, P1, we have 49.5 kilopascals, all right? So significantly less, all right? This one over here at P1, if it's 49.5, that means we're dealing with about half an atmosphere. So we're going from almost 10 atmospheres to a half atmosphere. Big pressure difference between the two. What is the flow speed in the pipe before it becomes narrow? All right, so that would be V2. And then what is the speed in the pipe in the narrow section, which would be V1. All right, so how do we go about solving that? Because all we know are the diameters and the pressures. Okay, so we're going to use continuity and Bernoulli. All right, so here's our continuity equation. All right, so let's go ahead and start with that. All right, so I'm going to say, okay, well, I want to just write this out in terms of what I know, I guess, first of all. And I'll go ahead and cancel out the pi's. This is just going to be pi r squared. I was given the diameter, which is why I divided the diameter by 2 to make it r. All right. Made sure to account for the fact that it's centimeters, so that cancels out on both sides. Okay, and I'm going to square it. And so let's go ahead and then solve, since we're interested initially in, before it becomes narrow, interested in V2, let's go ahead and solve for V1. All right, so this is V1 in terms of the ratio of the diameters. And see, look, that's because the 2's canceled. So it ends up just being the ratio of the diameters squared, all right, and then times the other velocity. All right, and obviously it's going to be D2 over D1 in order to get V1. All right, and again, that just comes from the algebra. All right, and I just I took the fact that these are both diameters, but I re-expressed them symbolically. And what we're going to do, though, is we're going to acknowledge that we don't know either velocity. So we can't actually solve this equation yet. So instead, we substitute this equation into the Bernoulli equation. Okay? So it's a substitution, because what we're dealing with is two unknowns, which is both the velocities and two equations. But we can't solve either of them directly because both the velocities show up in both of our two equations, continuity and Bernoulli. Okay? So then we're going to make a substitution, replacing V1 with this. That way we'll have the Bernoulli equation with only in terms of V2, and we'll be able to solve for V2. All right? So here I am. I'm just substituting it in. That's all I've done here. Notice I've just replaced the V1 term here with that expression for V1 in terms of V2. See? And I put the numbers back in, the 5.54 and the 2.07. Right here, I left V2 as is. I put in the appropriate densities. I put in the appropriate pressures that we were given. And I canceled out the hydrostatic term. Why did I cancel out the hydrostatic term? Because the height doesn't change. There's only one height. All right, so that's great. Okay, and then I go ahead and solve for V2 because that's my only unknown. All right, and I've just done the algebra here, expressed it, and there's my value. So before the pipe becomes narrow, when the speed is still slow, the velocity is 6.13 meters per second. And once I know V2 in part B, I can just really easily substitute it back into this relationship from continuity to find V1, and I get 43.9, quite a bit faster, which makes sense why, and that's actually pretty fast, right? Which makes sense why this pressure is much lower. Okay? There we have it. We've got how we would do an equation with no height change and two unknown velocities. Requires a bit of algebra, okay? All right, so now let's deal with one where there is a height change, okay? So here we have a large tank full of water with a density of 1,000 kilograms per cubic meter, right, standard water, and a cross-sectional area of 2.9 square meters, so that's the top. So we're not going to use Torricelli's theorem here. We're going to acknowledge that A1 is actually moving, or there is a velocity of the tank. It's slow, but there definitely is a velocity, okay? And all right. And so then that water level is lowering at a rate of 1 millimeter per second. That's this velocity. We'll call that V1. If a hose with a cross-sectional area of 4 square centimeters is attached to the bottom of the tank at a distance of 4.87 meters below the tank, okay, then what is the pressure in the hose? Okay, let's see. So here we're going to use continuity and Bernoulli, all right? And we're going to start by finding V2 directly. And the reason we can get away with finding V2 directly is we know both cross-sectional areas and we know one of the velocities. So there's only one unknown in the continuity equation, which is actually easier than the previous example. All right, so let's plug in our numbers here. Okay, we'll first do this solve for V2 from this equation, plug in our values, and there we go, 7.25 meters per second. Quite a bit faster than 1 millimeter per second, and that's because it's quite a bit narrower, right? And notice the velocity is only dependent on the change in cross-sectional area. Velocity is completely independent of the change in depth. The change in depth has no bearing on the velocity, which is so interesting, right? See that? Okay, look, the velocities are only dependent on the areas, okay? Now that we know the velocity, now we can answer the question about the pressure, because we weren't asked about velocity, were we? Okay, so then we go back to the Bernoulli equation. All right, I'm going to go ahead and solve for P2. I'm just solving for P2 by subtracting both these terms from the right side of the equation, and then rewriting it with P2 on the left for clarity. Okay, and then I combine like terms because I'm going to have my rho g term, which will be y1 minus y2, and then I'm going to have my 1/2 rho term with then v1 squared minus v2 squared. Okay, so let's look at this. Okay, so because there's an interesting story to be told here. This is just P1 after all is just atmospheric pressure. Okay, because the tube is open, right? P2 is definitely not going to be atmospheric pressure because it's inside an enclosed hose. All right, and then rho g is just 1,000 times 9.8. And then y1 minus y2 is just 4.87 minus 0, so it's just 4.817, or 4.87, excuse me. All right, and then our 1/2 rho, 1/2 1,000. And then we've got our initial velocity, our 1 millimeter per second, which is 10 to the negative 3, it's a millimeter, square it. And then our output velocity, which we found from continuity, 7.25 meters per second squared. So look, atmospheric pressure, adding pressure due to the depth, and then subtracting pressure due to the velocity. So these two effects, adding depth but making the hose more narrow and thus the fluid faster, they actually work against each other, right? So if the hose was even more narrow, thus creating an even lower pressure at the bottom, then these two effects could cancel out and we could actually maintain atmospheric pressure. But in this case, they don't. The effect of the narrow hose and the faster velocity isn't quite as dramatic as the effect of the depth, see, right? And so then we're still going to end up with an increase in pressure. We're going to end up with a pressure in the hose which is slightly greater than atmospheric pressure. And there it is, right? Not a lot greater, just about 22% greater, say 20% greater. Okay? And again, it's quite interesting. I hope that you see that the relevance of that depth adds pressure, but velocity removes pressure. Okay? All right, so it turns out the next example is really quite similar. I actually didn't quite think about that when I was choosing examples. It's really kind of all the same unknowns. The only difference is we're going uphill rather than downhill. All right, so one thing that is kind of noteworthy is we're given the density in terms of grams per milliliter. Well, grams per milliliter is like giving it in terms of grams per cubic centimeter, because a milliliter is actually equal to a cubic centimeter, right? Fun fact, okay? So then we have to convert the density from 0.807 grams per milliliter over to kilograms per cubic meter, and it becomes 807, okay? Good, there we have it. And it's liquid nitrogen. That is the actual density of liquid nitrogen, by the way. All right, so then you use continuity to solve velocity directly, just like the previous example. All right, working through, nothing new there, 1.36. All right, and the reason we were able to do that is because we were given the initial velocity, 4 millimeters per second, and then we were given the change in area, okay? And in this case, though, the velocity actually decreased because we went from narrow to wide, right? Which I guess is one other difference about this problem, all right? And then we're going to use Bernoulli to find the pressure, because that's what we wanted, was two things in this case. We were actually asked for the velocity, hence the square around it, and then we're asked for the pressure at the output. Okay, so we're asked for P2 and V2. All right, and so then here is the Bernoulli equation. We're going to solve for P2 just like in the previous example. All right, and if we look here, then we're going to be going uphill, which means we're going to be losing pressure due to going uphill. So this is going to be a negative term, and we're becoming here's the going uphill term. Here's the negative term. All right, and then but we're going to be gaining pressure from the fact that the fluid is slowed down. So these two terms are still working against each other, but in this case, the dynamic pressure is actually adding pressure to the system, and the hydrostatic pressure is removing pressure, because we've gone uphill, so this is a reduction, as obvious by the negative. And then since we've become wider and the fluid slowed down, this term is positive, so it's actually increasing pressure relative to our initial gauge pressure at P1. And our initial gauge pressure wasn't atmospheric, it was 12 kilopascals. All right? Okay, and there we go. And this is one where they almost cancel out. Look, the pressure at P2 is darn close to the pressure at P1, because the effects of gaining pressure due to becoming wider and the fluid slowing down almost exactly cancel out the effect of losing pressure because we went uphill. All right? And so do you think that people design for that? The engineers build systems where they compensate for height differences by pipe width difference? You better believe it. They do it in homes. They do it in buildings. All right? So when they go uphill, they use wider pipes in order to maintain one pressure throughout the building. Okay? Pretty neat. All right, so now on to our last two problems that represent the third type. So these are problems that involve continuity and Bernoulli, but then something extra. Okay, so in this case, it's projectile motion. So a person is holding a garden hose with a nozzle radius of 2.5 centimeters. That'd be the radius right here, right? Well, half the diameter. And a flow rate of 9.48 times 10 to the negative 4 cubic meters per second. Okay, so it's not a mass flow rate, that's a volume flow rate. All right, so that it is spraying water horizontally as shown. Okay, so initial velocity is entirely horizontal. It's at a height of 1.35 meters above the ground. What is the initial velocity of the water as it leaves the hose and the range of the spray before hitting the ground? Okay, well, let's see. So we're given the flow rate. Flow rate is volume times area, all right? So that's what we're given. So that means if I want to find velocity, I simply take flow rate and divide it by area. All right, so all I do is take the given flow rate and divide it by the cross-sectional area, considering the radius that I was given, and then assuming it's a circle. Okay, so then the velocity is 0.483 meters per second, or 48.3 centimeters per second. So see how I did that? Flow rate divided by area gives me velocity. Okay? Okay, hopefully it makes sense. And then this part is totally review. Since it's projectile motion, first of all, I want to find the time of flight, which is entirely based on the vertical displacement. Once I find the time of flight, then I'll multiply that time by the initial horizontal velocity to get the range. All right, so my time of flight ends up being about half a second, all right, because it only takes about half a second to fall a meter, all right, in this case, a meter and a third, all right, and then the range is then just going to be Vx times time of flight, which is 25 centimeters, all right, because it's coming out pretty slow, and so it's only traveling 25 centimeters, okay, all right, so, about a quarter of a meter, great, and the water's, this water's just kind of coming out at a steady rate, kind of coming straight down, hitting the ground, all right. Fair enough. Now in part 2, if you want to spray the water a distance of 2 meters because you want to water those plants across the garden, then what do? You cover up some of the hose with your thumb. All right? So what percentage of the nozzle area will you have to cover with your finger? Well, let's see. All right? So here the projectile motion part's the same. So I'm going to work backwards from projectile motion. Time of flight is definitely the same because it's the same height, right? That's projectile motion for you. So that means that if I want a certain range, if I want a range of 2 meters, that means I'm going to need a certain initial horizontal velocity. I'm going to need 3.81 meters per second, significantly faster than 0.483 meters per second. That's going to be what I call V prime. All right, then I'm going to put that V prime into the continuity equation because essentially I have the fluid coming in, the hose, I've got the person's finger here, and so the idea is there's some V, right? That's the initial velocity. And then there's some V prime much faster because the narrower section that is uncovered, that's left uncovered by the finger, right? That's the idea. That's the VA equals V prime A prime, okay? All right, so then we're going to solve for A prime because we already know V and V prime. We know V because it's this value, okay? And so then what do we get? Okay, so we'll take, in fact, you can we don't even have to even multiply V by A because we're given the mass flow rate, so we'll just take the value given, because after all, VA is, volume flow rate. So 9.48 times 10 to the negative 4 cubic meters per second, divided by our necessary velocity that we found from projectile motion. And then we get that the area, the uncovered area, okay, needs to be 2.5 times 10 to the negative 4 square meters, okay? That is definitely smaller than our initial area, okay? All right, let's find out how much smaller. Well, the change in area is the initial full area of the hose without any finger covering it, minus the new area, so that's the change in area, okay? So then, since we're asked for a percentage covered, it would be the change in area over the original total area times 100 to make it a percentage. There's the numbers, 87.3%. So we'd have to cover up most of the hose, just leaving, like a little bit, so it's squirting out really fast to get it to shoot 6 feet, right? About 6 feet or 2 meters. Okay? All right. Hopefully an interesting problem. I think it's an interesting problem. All right. So then when you're watering your garden next time, you can do some fluid dynamic physics to find out exactly how much of your hose to cover. All right? Well, good luck with that, right? Because in practice, there's some things we're ignoring, right? Like the turbulent flow. Okay. Or air resistance of the water once it's in the air. All right. So last one, example 6. All right. This is the one that's going to involve lift. All right, so why does fluid flow generate lift? Because it turns out that's how planes fly. They have flow at the bottom and flow at the top, and that difference between the pressures is where lift comes from. Fundamentally, Bernoulli's equation, at least at a basic level, explains lift for birds and planes. All right, so an airplane generates lift with its wings by having a cross-sectional shape that forces air to move faster over the top than the bottom. So if you have faster air over the top, that means you have low pressure up top, and you have what? Higher pressure on the bottom. Well, if you have higher pressure on one side and lower pressure on the other side, where do you think the force points? The force, of course, points towards the low pressure region. That's lift. It's pretty neat. So using an air density of 1 kilogram per cubic meter, and considering an airplane wing with a surface area of 15.8 square meters, how much lift force is generated by a single wing if the speed is 180 meters per second on the lower side and 240 meters per second on the upper side? Assuming the wing surface area is equally divided, so we can just kind of simply do a multiplication. Once we have the change in pressure, we can just multiply it by the area. Okay? So here's the velocity at the top, the fast velocity. Here's the velocity at the bottom, the slower velocity. They're both fast, right? But it's slower at the bottom. Okay? All right, so we're going to use Bernoulli to find the pressure above and below the ring. All right? So we're going to set up our Bernoulli's equation, but we're going to cross something out right away, something we haven't talked about. We're going to make the assumption that the wing is thin enough that there's no substantial change in height, no hydrostatic pressure that matters. And what makes this assumption like doubly reasonable is, first of all, yeah, wings are pretty thin. And second of all, the air is so low density that even if the wing was pretty thick, this would still be a tiny number compared to atmospheric pressure, and then certainly compared to the dynamic pressure, which is going to be driven by these large velocities, squaring big numbers, like squaring 180, right? Okay, so these terms are going to be so much smaller, they just don't matter. I mean, we'd be talking a fraction of percent error even if we were to consider that. All right, so that means that our delta pressure, just taking P top minus P bottom, all right, and this will give us a positive value because the pressure is going to be let's see. Well, no, the pressure is going to be less at the top, so this should give us a negative value. All right, and then we're going to have 1/2 rho velocity at the bottom. Oh, I see. Yeah, so this is actually supposed to be PB minus PT, and you can see the terms here. So in order for delta P to be positive, we have to take the pressure at the bottom, where it's greater because it's slower, minus the pressure at the top, where the pressure is less because the velocity is faster. And here you can see the correct subscripts. All right, so this should be B, and that should be T. Okay, all right. So we'll plug in the numbers, all right? So we are taking 180 minus 241, so 180 squared, okay? Shoot, I'm kind of going back and forth on this. I'm not being consistent, because here I end up getting the negative. But regardless, the magnitude is what matters, okay? So the magnitude is what matters. It doesn't, the fact that it's negative just tells us that it's pointing up, okay? All right, and so then we'll take the absolute value, because it is, like I said, it's the magnitude that matters, multiply by the cross-sectional area, just simply multiply by 15.8 square meters, all right? And by the way, the pressure difference that we got was 1.28 kilopascals, or 1.28 times 10 to, or actually 12.8 kilopascals, all right? So about just over 1/10 of atmospheric pressure, okay? But how much force does that give us? Oh, decent force, right? Gives us about 200,000 newtons of force. I don't know if it's enough to hold up a full-size plane, but it'll be enough to maybe, considering that it's one of two wings, this can maybe hold up a small plane. Okay, so there we have it. This is where lift force comes from using Bernoulli's equation. Right, some simplification, sure, right, but still a good thing, because it's an open question, like where does lift come from, right? It comes from fluid flow, variations of pressure. All right, but ultimately, this whole lecture has been about flowing fluids and its effects on pressure and velocity. Okay, well, I hope it's been interesting and informative. Thank you for watching.